Okay, where you're going. So, hi, my name's Brandon.
My name is Andre.
Hey, I'm Eli.
Awesome, we'll go ahead and jump right in. Eli, you
All
want to
right.
start us off with number 4?
Yep. I'll start us off with number 4, which is so we're taking derivatives of the function u of x, which is u of x is g of f of x, and so to take the derivative, we're going to use the chain rule, and it's going to go to the derivative is going to be g prime of f of x times f prime of x. And so for item 4, it wants it to be, we're plugging in 4. And so we got to look at the graph and find what it is at 4. And so we're going to have, so g prime of 4 of x. And so 4 is 3, and then, or f of x at 4, at 4 is 3. And so we're going to get g prime of 3 times f prime of 4. And so f prime of 4 is 3, but or f prime of 4 is also 3, and then g prime of 3 is like undefined at 3. And so basically the answer just becomes undefined because of that, because it's multiplied by the 3. And so basically the calculus we use here is just the chain rule in the beginning to take the derivative, and then we're just analyzing the graph for the slope and the points.
All right, so for number 12, which is our next problem, it is asking us to find the linearization of the equation y equals x to the x power to estimate nonlinear function value at the or around the point 1, 1. And we're estimating for the y value of 1.25. So what we do first is I'll let you get to the work. So we use the linearization formula, which is going to come out to L of x is equal to f of a, which is your input, plus f prime of a, the derivative, times your output minus a, or sorry, your input minus your output. So after that, for the f of a, we're going to input, because we're given 0.11, we're inputting 1. For f prime of a, we're taking the derivative of that input, which is also going to come out to be 1. And then for x minus a, we have our x value minus just the function value, which is also going to come out to be 1. And then the 1's cancel out. The derivative function and the input of the regular function cancel out to leave us with x. So then we have L of x equals x. And then our input, what we're estimating for, is 1.25. And then basically what we put in is going to be our output, because L of x equals x. So we put in 1.25, and our approximation is 1.25 for the output.
Awesome. We'll go ahead and go to 16 and 17.
Yep. All right. So, sorry, I'll wait for you. Okay. So for 16 and 17, it's asking us to estimate, so estimates of x that satisfy the mean value theorem for the closed interval on 0 to 8. And so basically, we just follow the rules of, or we just follow the mean value theorem. So we have to first make sure it meets the two conditions, which is if the function is continuous and if it's differentiable, and it is both continuous and differentiable on the on the interval 0 to 8. And then after that, I just had to look for I just had to look through the math and then find the secant and tangent line that would be parallel. And so doing that, we got 6.25 from the tangent line and 3 and 8 from the secant line. and those, if you look at those on the graph, those come out to be parallel.
Awesome. All right, so I'll go ahead and do 21. So 21 says that the graph of a function is given below. Suppose that Newton's method is used to approximate the solution of an equation with initial approximation at x1 is equal to negative 0.75. Draw the tangent line that uses x1 and then determine x2. Then draw the tangent line at x2 and draw these two tangent lines neatly to determine x. So what I did here is got x1 is negative 0.75. So I found that point on the graph, which is right about here, and I graphed the tangent line, just kind of eyeballed it, and then that gave me the right number to plug into the Newton's method formula, which is right here. X to whatever plus 1 equals xn minus f of xn over f prime of xn. So if x1 is negative 0.75, x2 is going to be negative 0.75 minus negative 0.3 and over negative 1, which is going to give us x2, which is negative 1.05. So then I draw that on, to write that down here, and then I find negative 0.05, and then I graph the tangent line at that point, and then just kind of guess what its derivative is based on the tangent line, which you can get pretty close by just looking at it to figure out x3. And doing the exact same thing with Newton's method here. This is what x2 equals, negative 0.105, so you'd plug that in for x3 is going to be negative 1.05 minus 0.1 over negative 2. And so x3 is going to be negative 1. So x3 is negative 1. So here, to validate this, it's already telling us what kind of math we're doing here, what type of calculus we're doing. Is Newton's method. Well, Newton's method is to approximate the x-intercepts or the zeros of the graph using just looking at the graph, and if it's kind of in not that neat of a spot, you can graph the tangent lines and then plug into Newton's method to find it out, which I came up with negative 1, which is either right on or really close to it, so that's going to be good enough there. With just using Newton's method and just tangent lines, I feel like that's a very cool aspect. That's it for that. We'll go ahead and do apply 1, which is also me. Awesome. So the apply section for item 1. So it says to consider the following problem. A box with an open top is to be constructed from a square piece of cardboard 3 feet wide by cutting out the square from each side of the 4 corners and bending up the sides. Find the largest volume that such a box can have. So right here, find the largest volume is telling me that we're going to be using optimization. We want to optimize the largest volume for a box given these parameters. So A tells me to draw several diagrams to illustrate this situation. Some short boxes with some large bases and some tall boxes with small bases. Find the volume of several boxes. Does it appear that there's a maximum volume? If so, to estimate it. So what I did was draw each box. I draw 4 just to demonstrate the boxes of what it could be, and labeled them with width, length, and height, each one. And then I declared my variables here, and I stated that this does appear to have a maximum volume. I'm going to estimate about 3 feet cubed, given that the entirety of the cardboard box is only 3 feet wide. I was just throwing it out there. So B says to draw a diagram illustrating the general situation and then introduce notation and label the diagram with your symbols. So for my symbols, I chose to use X and Y, X being the length and the width because the base is square, so each side is going to be the same, and Y being my height. So it's taking a flat cardboard box, which I illustrated here with dotted line all the way around, and then cutting out the corners. So these corners are getting cut out all here. So really all you have is this weird looking shape here. And I started labeling everything. If X is the length and width, then X, Y, all these things are getting labeled as right here. So that's for part B. So part C says to write an expression for the volume. I know volume is going to be equal to length times width times height. When width, that's basically saying if X is the length and width, it's telling me that X times Y is equal to volume, which is X squared times Y. For D, it says to use the given information to write an equation that relates the variables. So one thing that can relate the variables is actually given to us. We know that the cardboard is 3 feet wide. So this right here is going to be 3 feet. So y plus x plus y is equal to 3, which I shortened it out to be 2y plus x is equal to 3. Then E says use part D to write the volume as a function of one variable. So I can take my 2y plus x is equal to 3 and just solve it for x. So x is going to be equal to 3 minus 2y, and then plug that into my volume to get rid of my x value. So now volume's going to be just in one variable, which will then allow me to solve this problem. So F. Finish solving the problem and compare the answer with your estimate. So in part F, I say that the volume is equal to the quantity of 1 minus 2y squared times y. So for optimization, I know that you're supposed to take the derivative of this. That's actually a 3 minus 2y. I messed that up. Take the derivative of this and then set it equal to 0. So I take the derivative of my volume using the chain rule and the product rule, which not necessarily all that easy, but got it done. And came out to be 12y squared minus 24y plus 9. I realized that I could just take out a 3 by dividing the entire equation by 3 to just simplify it a bit more for me. So 4y squared minus 8y plus 3 is equal to 0. And then I could factor out a 2y, and then that's going to give me two possible y values to which it would maximize the volume. So either y could equal 0.5 or y could equal 3 halves. So I plugged in each one to my volume equation over here, and comes out that if I plugged in three, if I plugged in 3 halves, that I would get a 0 for my x. And well, the height can't be 0 to have a volume, so I knew that that cannot be it. So I plugged in my 3 halves. 3 halves is going to give me, oh, I said that backwards. 3 halves is going to give me 0 for x. 0.5 is going to give me 2 feet. 3 halves cannot work, but 0.5 or 1 half does work, giving me a maximum volume of 2 feet cubed. And I was pretty close in my estimate here. I said 3, I actually got 2, so I was only 1 off. But the calculus behind this is simple, just optimization by finding an equation for my symbols and then finding another equation that will relate my symbols and then to get my my constraint into a into one variable so I can solve for it. And this can be applied to most optimization problems, even if it wants a minimum. That's that.
All right.
Boom.
So moving on to apply number 2. This is going to be a long one, so buckle up. First, basically what this question is asking is, or we're given the position function of a particle, and we're supposed to basically determine like the velocity, the acceleration, and then different points along the way, like when it's decreasing or increasing, things like that. So first thing I did of this was write out the equation and declare my variables. Our equation is going to be the position of a particle is equal to e to the negative t square root of t, where t is going to be greater than 0. And then t is going to be our seconds, and s, which is what that equation is equal to, is going to be the meters traveled by the particle. So for part A, it asks to find the velocity at time t. So I have here f prime of t is equal to the derivative of e to the negative t square root of t. So what I need to do here is use the product rule, which is going to be the derivative of the first term e to the negative t times square root of t, the second term, plus e to the negative t uh, times the derivative of the second term, which is going to be square root of t. And that comes out to negative e to the negative t square root of t plus 1 over 2 square root of t times e to the negative t. And for that second part there, what we need to do is simplify after that. So we're going to combine the 1 and the e to the negative t. So it comes out to f prime of t is going to become negative e to the negative t square root of t plus e to the negative t over 2 square root of t. So that's going to be our function to find velocity of this particle. For part B, what's the velocity after 0.25 seconds and after 1 second? So this one was simpler. All I needed to do was plug in these two uh, these 2 points to the function and evaluate them at those points. So for the first one, I got 0.3894 meters per second. For 0.25, for 0.25 meter at 0.25 meters, it was moving 0.3894 meters per second, and then at 1 meter moved, it was moving negative 0.1839 meters per second. For part C, it asks when is the particle at rest. So in the velocity function, that's basically when is the graph going to hit 0, which means that it has no motion in one direction or another. So I found that at 0.5 seconds by basically evaluating for 0 meters per second and then solving backwards to find what the input would be, which comes out to 0.5 seconds. For part D, when is the particle moving forward in the positive direction? So that's going to be before it comes to a stop, it's moving positively. And then we found out that at 0.5 seconds, it stops its motion. So from 0 seconds to 0.5 seconds, it does have that positive motion. And in a second, I'll get to the graph where you can visually see that it is positive and hits 0 right at 0.5 seconds. For part E, draw the diagram to represent the motion of the particle. So right there, I've got a small scale graph where you can see that this is the graph of the velocity. Starts out in a positive direction, and then right at the 0.5 where I evaluated, it hits 0, and then goes into a negative velocity, where we also see earlier in the problem. And then for F, find the total distance traveled by the particle during the first 2.5 seconds. So for that one, I use the distance formula, which is what I have to do is take the square root of x2 minus x1 squared plus y2 minus y1 squared. So I plugged in because it gives us our 2.5 for the input. I evaluated, give me 1 second. Okay, so I evaluated at 0 and I evaluated at the 2.5 seconds that it gave to us. So at 0, the distance of the particle was going to be, of course, 0 meters because it hasn't moved yet at the 0 seconds. And then at the 0.25 seconds, it was going to be 0.1298 meters traveled. So I plugged each of those, the x2 2.5 and the x1 0 squared. That's going to come out to 6.25. And then I plugged in the y2 0.1298 and the y1, which is also 0, and then squared that, and that gave me 0.016848. And then evaluated that, took the square root, and it came out to 2.5034 meters at the 2.5 seconds. And then for part, let's see, G, I had to find the acceleration at time and after 1 second. So in order to do that, I also had to find the function for acceleration, which was going to be the second derivative, taking the derivative of the velocity function. So in order to do that one, I had to use the sum and difference rule. So I'm plugging in the, let's see here. So I'm plugging in the derivative of e to the negative t square root of t, and then setting that equal to negative e to the negative t plus e to the negative t over 2 square root of t. And then I am taking the derivative of e to the negative t over 2 square root of e and setting that equal to negative 2e to the negative t plus e to the negative t over 4t square root of t. And then that gave me, I just wrote it backwards, I guess, but I put the function for acceleration up at the top. So it's going to come out to negative 4e to the negative t times t minus e to the negative t plus 4e negative t squared. Oh, sorry, t squared. All that divided by 4t square root of t. So that was only finding the acceleration function, and it asked me to find the acceleration at and after 1 second. So in order to do that, I plugged in 1 second to that function and came out with negative 0.092 meters per second squared of acceleration at 1 second. And then afterward, I demonstrated that by it's going to be greater. The acceleration is going to be greater because as we plug in higher values, the output increases. So it's going to be greater than negative 0.092, but it's also going to be less than 0 because the acceleration never reaches 0 on the graph. And then for part H, using Desmos, graph the position, velocity, and acceleration functions for the first 2.5 seconds. So the purple line is going to be your position function. The blue line is going to be your velocity function, and then black is going to be acceleration. And you can see how those correlate each as they kind of hit the zeros and then all trend back to the 0 line because it's all decreasing. And then let's see. For part I, when is the particle speeding up? When is it slowing down? How do you know? So the particle is going to be, I use the velocity function to determine this one. It is slowing down first until t equals 0.5 seconds or half a second because it's going from a positive to a full stop and then and then moving on into a negative velocity. So it's slowing down and then hits 0 at 0.5 seconds and then speeds back up after that as it hits negative velocity. because my f prime derivative function is going to be negative after that 0.5, which means that it's speeding up, and then before that it's slowing down because it comes to a stop at the 0.5.
Awesome. And the calculus you're using here is like just knowing the difference in higher derivatives.
Yeah. So first, in order to find my first derivative, just basically using the product rule, plugging that function um, into the product rule, and then for the second one, acceleration function, because there's a sum and difference there from the first derivative, I'm using the sum and difference rule.
Yeah, so the original function and then the derivative of the original function's velocity and the derivative of velocity is acceleration and so on.
Yeah.
Awesome. I think that's it. I'll go ahead and stop this.